Okay, so now let us talk about the L'Hopital rule now. Okay, now the L'Hopital rule is actually a rule to help you to work with the limits of a function over another functions. Okay, so this is actually is sometimes it is really hard to do some of the limit evaluation, right? However, then this L'Hopital rule will help you to make it easier to find the solution then. However, there are some condition that we need to follow here. Suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval I that contain a. Suppose that the limit x approaching to a of f of x equal to 0 and the limit x approaching to a of g of x equal to 0, or the limit of f of x is positive or negative infinity, and the limit of g of x is positive or negative infinity. In other words, we have an indeterminate form of the type of 0 over 0 or infinity over infinity. It doesn't matter if it's positive or negative infinity over positive or negative infinity then. Then in this case, we have the limit x approaching to a of f of x over g of x is equal to the limit x approaching to a of f prime of x over g prime of x, if the limit on the right side exceeds. Now, here is the L'Hopital rule. Remember, the L'Hopital rule is not a quotient rule. We are not applying the quotient rule. Basically, what we do is just say that if we have a limit of f of x over g of x, it is the same as the limit f prime of x over g prime of x. So basically, we just take the derivative of the f functions over the derivative of the g function then. Okay, so this is the idea about the L'Hopital rule. Okay, now note the L'Hopital rule say that the limit of a quotient of a function is equal to the limit of a quotient of their derivatives. Okay, provide that the given condition are satisfied. Okay. Okay, so then now I'm not going to prove it. Okay, so you could actually look at the textbook, and then there's a simple proof to say that. Okay. Okay, now here is really important. Whenever you want to use a L'Hopital rule, make sure that you always verify the conditions. The condition is here, the indeterminate form. Okay. Okay, so let's try to find the limits now. Using a L'Hopital rule, if there is a more elementary method, consider using it. Okay, if the L'Hopital rule doesn't apply, explain why. Okay, so let's try this. Okay. Okay, so now then let's look at our first example. Okay, now to the first example, if we want to evaluate, okay, meaning by direct substitution, right? I have 2 squared plus 2 minus 6 over 2 minus 2. Then we know that it is 0 over 0. So indeterminate form. Then in this case, then what we could do here is we could actually apply the L'Hopital rule, and then we could take the limit x approaching to 2 of 2x plus 1 over 1. Then, right? Okay. Then now, what we could do here is we could actually just using direct substitution, then we have 2 times 2 plus 1. So the answer is equal to 5. Okay, that's it. So this is how we use the L'Hopital rule. Okay, now let's check to see if this is the case now. So in this case, now remember we, maybe let me use a different color here. Okay, now back to chapter 2. Then we have learned that to this one right here, basically we could factor. So I will have 2x plus 3 and x minus 2 over x minus 2. So therefore, in this case, we have 2 plus 3, which is equal to 5. Okay, so now you will see that we get the same result. Okay. Okay. Then now, how about this number 2 right here? Then, of course, we could actually try to evaluate now. Sine of 0 over tangent of 0, then, of course, we know that it's 0 over 0. Again, indeterminate form. Then, in this case, what we could do here is we could apply the L'Hopital rule. Then the derivative of sine of 4x, which is 4 cosine of 4x, all over 5 secant square of 5x then. Okay. And then now, of course, we could use direct substitution, right? So I have 4 cosine of 0 over time over 5 secant of 0 square. Okay. And then we know that cosine of 0 is 1, secant of 0 is also 1. So my answer will be 4 over 5 now. Yeah. Okay, so then let's try another one. Okay. Now to this one right here, then again, let's check this out. Okay. Then we have infinity, so infinity square over -2 times infinity square. So I will have infinity over negative infinity. Okay, which is indeterminate form again. Okay. Then now what we could do is we could apply the L'Hopital rule. So I have the limit x approaching to infinity of 2x plus 1 over negative 4x. Okay. Then now we could check it again. So we have infinity over negative infinity. Okay. So then now we could apply another L'Hopital rule. Right. Then I will have 2 over negative 4. Okay, so then in this case right here, then I will have the answer will be -1/2 then. Okay, yeah, this is exactly what we have. Okay, then now to this one. Okay, then let's check this out. So we know that when x approaching to infinity, so the natural log of infinity is infinity over infinity now. Okay. And now we could apply the L'Hopital rule. So I have the limit x approaching to infinity. Oh, maybe before we apply the L'Hopital rule, then let's try this. So I have 1/2 natural log of x over x squared. Okay, just simplify it first, right? And then now I could have the limit x approaching to infinity of 1/2. Oh, now I apply the L'Hopital rule. Multiply to 1 over x over 2x. Okay. And then now what we could do here is we could actually simplify this first. Okay, so I will have 1 over 4 and then multiply to 1 over x squared. Okay. Okay, then now we know that when we apply the infinity here, when limit x approaching to infinity, this becomes 0. So my answer will be 0 then, right? Yeah, so this is actually the idea about the L'Hopital rule. Okay. Now, how about the next one right here? If we have a product f times g, while the indeterminate form is 0 times infinity. Now, one thing about this is you have to remember 0 times infinity is not infinity or it's not 0. Okay, so it's something that we don't know. So therefore, in this case, what we could do is actually we could rewrite the form of the f times g, okay, into a kind of like quotient right here. And then from there, then we could apply the L'Hopital rule to finish the problem then. Okay, so then let's try this one right here. Okay, so then let's check this out. When x approaching to negative infinity of x squared, of course we know that this is infinity. However, to this one right here, remember to e to the x, then when x approaching to negative infinity, which is 0, right? So then now, wow, we know that we have an indeterminate form is infinity multiplied to 0 then, right? Okay, so what we need to do is, again, we are going to rewrite this into a, a quotient, okay? So in this case one here, what we could do is actually we could rewrite it into this form, is the x squared over 1 over e to the x then. Okay, then now what happened here is, okay, so I will have x squared over e to the negative x. Then now, if we apply the L'Hopital rule, then I will have infinity over infinity now. Okay. Okay. Then what we could do is we could apply the L'Hopital rule then. And I will have 2x over negative e to the negative x. Okay, so in this case, again, if we check 2 times x is negative infinity over negative infinity. Then now we could actually apply another L'Hopital rule. Okay. And then in this case right here, we will have 2 over e to the negative x. Okay. And of course, now if we direct substitution, then we will have 2 over infinity. So therefore, the answer in this case, it will be 0 now. Okay. Now, of course, maybe some of you feel that, how about if I want to do it this way? That means I keep the e to the x and then x to the negative 2. Okay. Now, check this out to see what happened here. If we apply the L'Hopital rule, then what happened? We have e to the x, and then to this one right here, we will have negative 2 e to the negative 3. Okay. Now you will, oh, I'm sorry, not e, but x, right? Okay. And then now you will see that what happened here is actually you are going to have a always to this one right here. Then you will see that you always have 0 over 0, 0 over 0. Okay, if you keep doing the L'Hopital rule, you still always got 0, 0, and then it won't help you to solve the problem. So therefore, in this case, okay, so of course you have to maybe try, okay, so when you have f times g, okay, so you need to try which one is the one that we need to work with, is 1 over g or 1 over f. Then. Okay. Okay. And now, how about this one right here? Okay. So again, to this one, we will have infinity multiplied to tangent of 0, which is 0, right? Again, indeterminate form. So to this one right here, it seems that what I'm going to do here is I would like to rewrite this into something like tangent of 1 over x all over 1 over x. Okay. Okay. So if this is the case, then I will have 0 over 0 now. Okay. Then I'm going to apply the L'Hopital rule. Then I have the limit x approaching to infinity of sine square of 1, oh, not sine, but secant, right? Secant square of 1 over x, and then I take the derivative of 1 over x. And the denominator, again, I also need to take the derivative of 1 over x. And then you will see that what happened here is these two, they cancel it. So then now I actually have the limit x approaching to infinity of secant square of 1 over x. Then, of course, we know that to this one, the secant of 1 over infinity, which is 0, secant of 0 is 1, so 1 square is 1. Okay. Now the next one is actually is how about if we have infinity minus infinity? Okay, so now remember infinity minus infinity is not equal to 0. Okay, so then in this case, what we need to do, basically, if we have two terms, then maybe let us combine it to make it a one term. Okay, so like this one, then I will have 1 over psi of x minus cos of x over psi of x then. And then I will have the limit x approaching to 0 of 1 minus cos of x over psi of x. Oh, by the way, I should evaluate this way. Now cosecant of 0 is infinity. Cotangent of 0 is also infinity. Okay, so then again we have infinity minus infinity. Okay, so then we continue. Okay, so then now we have the limit x approaching to 0. Oh, let's check this out. So we will have 1 minus 1 over 1 over 0. And again, it is 0 over 0. Okay. And now we apply the L'Hopital rule here. Then I will have this one is psi of x over cos of x. And of course, we know that here I have the limit x approaching to 0 of tangent of x then. Okay. And of course, I know that tangent of 0 is equal to 0, right? Okay, so let's try number 8. Okay, so to this one, again, you will see that cotangent of 0 is infinity minus infinity. Okay, so we told. So, and of course, again, we could not apply the L'Hopital rule because the L'Hopital rule only when you have a quotient, then we could do it. So what we need to do is, again, we are going to combine this. Okay, so I need to have a cotangent is actually it will be cosine of x over sine of x minus 1 over x. Okay. Then it is equal to the limit x approaching to 0 of x times cosine of x minus sine of x over x times sine of x. Okay. And then of course you will see that then x0 minus sine of 0 is 0 over x is 0. So again, I have 0 over 0. Then I could apply the L'Hopital rule now. Okay. And then this, remember, is a product. So I need to work with the product rule. So I have to take the derivative of x, cosine of x, plus the derivative of cosine of x times x minus the derivative of sine of x. Okay, same thing here. The derivative of x times sine of x plus the derivative of sine of x times x. Okay. Okay. And now let's try to simplify this then. So I will have cosine of x minus x times sine of x minus cosine of x all over sine of x plus x times cos of x. Okay, then now you will see that to this one, basically we have cos of x minus cos of x. Okay. Okay, so I will have negative x sub x all over sub x plus x times cos of x. Okay, and then again we will have 0 over 0 plus 0. Okay, okay, apply another L'Hopital rule now. So I will have negative of the derivative of x. I just take the derivative then. All over, this one will be cos of x minus x times cos of x. Okay. Cos of x minus x times cos of x. Okay. Then now I will have negative psi of x minus, maybe just direct substitutions. So I will have negative psi of 0 plus 0 times cosine of 0 all over, this one will be 2 times cosine of 0 minus 0 times psi of 0. Then in this case, I have 0 over 2, which is equal to 0 then. Okay. Okay, so again, if you have two terms, okay, then try to see if you could rewrite this into a single term, okay, by completely just revoke the fraction then. Okay, now the last one is actually what if we have a functions, raised to the power functions. So again, in this case right here, the indeterminate form will be 0 raised to the power of 0. Again, remember it's not 1. 1 raised to the power of infinity. Now remember this is not 1. And then again, infinity raised to the power of 0. Again, it's not 1. Okay. So it just, we cannot determine it. Okay. Then if this is the case, what we need to do is we could actually follow this, that f raised to the power of g is the same as e times g, e raised to the power of g times natural log of f then. Okay. So now if you don't remember this, if you remember that a to the n, a to the x is the same thing as e to the natural log of a to the x. If you remember this, then this is exactly how we rewrite this. Okay. So this is actually is the idea. Okay. So you could go back to the logarithm. Okay. Look at the properties. Okay. So then now let's try this. So I have the again, if I use direct substitution, then I have 1 raised to the power of infinity, right? So indeterminate form. So what I need to do here is I would like to rewrite this into the limit x approaching to 0, e raised to the power of natural log of 1 minus 2x raised to the power of 1 over x. Okay, so then now we will have the limit x approaching to 0 of e to the 1 over x natural log of 1 minus 2x then. And now, what we could do here is, okay, so you have to remember that if this is the case, then we could actually evaluate e raised to the power of the limit x approaching to 0 1 over x natural log of, maybe let me rewrite into this form. Okay, so now this is what we want to do is try to evaluate this then. Okay. So if I have the limit x approaching to 0 of natural log of 1 minus 2x over x, then in this case, we know that we have direct substitution, then I have natural log of 1 over 0, which is 0 over 0, right? Indeterminate form. So then I could apply the L'Hopital rule here. Okay. So I will have 1 over 1 minus 2x, and then I take the derivative of 1 minus 2x over 1. So I will have 2 negative 2 over 1 minus 2x. Okay. Then now, if I direct substitutions, then basically my answer will be negative 2. Then, of course, in this case, my answer will be e to the negative 2 then. Okay, so then now it is your turn. Now go ahead and try this one right here. Okay. Okay, so same thing. I take the limit x approaching to infinity of e to the power of natural log of e to the x plus x raised to the power 1 over x. Okay. So I have e to the 1 over x natural log of e to the x plus x. And of course, you can have e to the limit x approaching to infinity of natural log of e to the x plus x over x. Okay, so then now I will have the, again, the limit x approaching to infinity of natural log of e to the x plus x over x. Okay. Then you will see that to this one, basically we have infinity over infinity. So then we apply the L'Hopital rule, then I will have over e to the x plus x over 1, right? Okay, so then the derivative of e to the x, just e to the x plus 1 over e to the x plus x then. Okay. And of course, now we still have infinity over infinity. So we apply another L'Hopital rule. Then I take the derivative of e to the x over e to the x plus 1 again. We apply another L'Hopital rule here now. E to the x over e to the x, which is 1. And now my answer is e. Okay. Or e to the 1. Okay, so then this is actually the idea about the L'Hopital rule. So again, the L'Hopital rule is work with the indeterminate form, like 0 over 0, infinity over infinity, like infinity minus infinity, or 0 raised to the power of 0, 1 raised to the power of infinity, or infinity raised to the power of 0. Okay, so if you have those forms, make sure that you are going to rewrite the expressions and try to apply the L'Hopital rule to see if you could get the result then. Okay, yeah, thank you.